The trajectory of this object is very peculiar. It actually lies in the orbital plane of the planets around the Sun, within 5 degrees or so. And that is a coincidence that has a chance of 0.2%.
Something unusual is happening close to home in our solar system. Astronomers have just spotted a mysterious object moving at high speed, and it clearly didn't originate here. Officially named 3I/ATLAS, this object is now considered only the third confirmed interstellar visitor we've ever observed passing through our solar system.
3I Atlas was discovered on July 1st by the NASA-funded Atlas survey. It was discovered using their telescope at Rio Hurtado in Chile, and it was first detected as a speck of light moving relative to background stars.
First detected in late June 2025, this strange object has stirred up serious interest and discussion in the scientific community. Its size, speed, and unknown nature have left experts both excited and confused. Some are even exploring possibilities that sound more like science fiction. What exactly is this object? Where did it come from? Could it be something more than just another chunk of rock drifting through space? Let's go over the latest findings on 3I/ATLAS, track its path, and see what sets it apart from anything we've seen before. The story starts with what was supposed to be a routine sky survey. Between June 25th and June 29th, 2025, the Asteroid Terrestrial Impact Last Alert System, known as ATLAS, noticed something that stood out. ATLAS uses a group of powerful telescopes in Hawaii and South Africa to scan the skies for anything unusual, including asteroids and comets that might pose a threat to Earth. These telescopes automatically search the sky each night and collect data on all kinds of space objects. In late June, one faint light caught the system's attention. It was given the temporary label A11PL3Z. At first, astronomers weren't sure what it was. Was it a comet, an asteroid, or something else altogether? What puzzled them most was the object's trajectory. It was far too straight and fast to be from within our solar system. That pattern hinted at an interstellar origin, suggesting this object had come from deep space. The discovery didn't stay quiet for long. By July 1st, 2025, NASA's Center for Near-Earth Object Studies at the Jet Propulsion Laboratory, along with the International Astronomical Union's Minor Planet Center, confirmed the object was indeed interstellar. A11PL3Z was then given its official name, 3I/ATLAS, or C2025N1. The 3I designation means it's the third interstellar object ever confirmed, following 1I/Oumuamua in 2017 and 2I/Borisov in 2019. Paul Chodas, the director of the Center for Near-Earth Object Studies, put it plainly. "This thing is travelling pretty fast," he said. "There's no uncertainty that the comet came from interstellar space, with its speed measured at around 152,000 miles per hour relative to the Sun. Right now, 3I/ATLAS is located about 420 million miles from us. That's around 3.8 times farther than the distance from Earth to the Sun. Its path shows it's just passing through, with no chance of returning." One of the reasons scientists are paying such close attention to 3I/ATLAS is its size and strange appearance. Early measurements suggest the object could be as much as 12 miles, or 20 kilometers across. If this turns out to be correct, it would be much bigger than both Oumuamua, which ranged from 100 to 1,000 meters long, and 2I, Borisov, which was about 1 kilometer in diameter. Harvard physicist Avi Loeb, who has played a big role in the study of interstellar objects, noted that 3I/ATLAS appears unusually bright given its distance. In astronomy, brightness can indicate either size or how reflective the surface is. If this object has a dark, rocky surface like most asteroids, then it must be extremely large to be reflecting that much sunlight, hence the 12-mile estimate. Still, Loeb has also warned that it could be misleading. If it's a comet, it might just have a small core with a large surrounding cloud of gas and dust, which would make it seem bigger than it actually is. Right now, scientists are still unsure if 3I/ATLAS is a comet, an asteroid, or something else. To see why this discovery matters so much, it helps to look back at the two interstellar objects found before this one. The first was one I/Oumuamua, discovered in October 2017 using the Pan-STARRS telescope in Hawaii. Its name means a messenger from afar arriving first in Hawaiian, fitting for the first known object from another star system. Oumuamua didn't resemble anything astronomers had seen. It was small, somewhere between 100 and 1,000 meters in length, and shaped in an unusual way, either like a cigar or a flattened pancake. Its red color pointed to a surface exposed to cosmic rays over millions or billions of years. The most confusing part was what happened after it passed the sun. The object started accelerating, and this movement couldn't be fully explained by gravity alone. Comets usually gain speed due to outgassing, when sunlight heats them up and releases gas and dust. But Oumuamua didn't show any visible tail or coma. This led to all sorts of theories, with Loeb famously suggesting it might not be natural at all. Maybe even a probe or abandoned spacecraft sent by an alien civilization. The second visitor from interstellar space was 2I/Borisov, which was found in August 2019 by Gennady Borisov, an amateur astronomer. Unlike Oumuamua, this object clearly behaved like a comet. It had a visible tail and shared chemical traits with other comets in our solar system. It approached from the area of the Cassiopeia constellation and reached its closest point to the Sun in December 2019, when it was around 180 million miles from Earth. This discovery proved that objects from other star systems could pass through our own more than once. The difference this time was that our tools had finally become good enough to detect them. Now that 3I/ATLAS has appeared, scientists have a third example to work with, and more questions to answer. Why are we suddenly noticing these visitors now, after so many centuries of silence? Have they always been coming through, but we didn't have the technology to see them? Or is something different happening in our part of the galaxy? The direction 3I/ATLAS came from offers some hints. When researchers traced its course backward, they found it likely originated near the center of the Milky Way. While we can't determine its exact source, it's probably been moving through interstellar space for hundreds of millions or even billions of years, not attached to any star system. Its hyperbolic orbit, with an eccentricity of about 10.4, confirms that it doesn't belong to our solar system. Most solar system objects follow elliptical orbits with eccentricities below 1, allowing them to loop around the Sun repeatedly. In contrast, the extreme shape of 3I/ATLAS's orbit shows that it's making a one-time pass, zooming through our solar system before heading back out into deep space. The object's closest pass to the Sun, its perihelion, is expected to occur on October 29th, 2025, at a distance of about 1.4 astronomical units, AU, which is around 1.4 times the space between Earth and the Sun. Then, on October 30th, it will come within 1.35 astronomical units of Earth, remaining safely positioned on the opposite side of the Sun. By December 17th, 2025, it's expected to make its closest approach to Earth at approximately 2.4 astronomical units, a distance that still keeps it well out of harm's way. Astronomers are paying close attention to the size estimates of 3 3I/ATLAS. If it truly measures around 12 miles across, it would be significantly larger than both Oumuamua and Borisov, placing it among the largest interstellar objects discovered so far. For comparison, something that size would be about as wide as a small city. Still, appearances may not be reliable. Objects like comets can appear brighter due to a surrounding coma, a glowing cloud of gas and dust that forms when they approach the sun. If 3I over ATLAS turns out to be a comet, the solid core might only span 1 or 2 kilometers, while the rest of the visible size comes from that halo of debris. Initial observations point toward it being a comet, which is how the Minor Planet Center has classified it. However, some researchers believe it might be an asteroid because it lacks a clear coma or tail. To help clarify this, astronomers are collecting more data as quickly as possible. Observatories across the globe, including the highly capable James Webb Space Telescope, are now focused on studying 3I/ATLAS to better understand its makeup and behavior. Avi Loeb, known for exploring unconventional ideas, has recommended using the James Webb Space Telescope to check for non-gravitational acceleration, something also noticed with Oumuamua. This kind of motion happens when an object doesn't follow a path, explained by gravity alone, which could suggest things like outgassing, propulsion, or some other unknown factor. Most researchers believe there are natural causes for this, such as evaporating gas or ice, but Loeb's theory keeps more unusual possibilities on the table. Could 3I/ATLAS be a relic of some advanced civilization? A probe, perhaps, sent from another star system? While that idea may sound speculative, it's not completely ruled out. The object's surprising brightness and large estimated size make it a strong candidate for close investigation, and any strange behavior would only lead to more questions. The timing of its discovery has worked in scientists' favor. Unlike Oumuamua, which disappeared from view just weeks after being spotted, 3I/ATLAS remains far enough from the Sun to be visible for several more months. By late September 2025, it will move too close to the Sun's glare to be seen, but by December it should become visible again, giving researchers more time to observe. A major breakthrough could come from the Vera C. Rubin Observatory in Chile, which will officially start operating in 2025. Its 8.4-meter Simoni survey telescope will scan the entire night sky every few nights, making it possible to detect faint and fast-moving objects like 3I/ATLAS. Even during a short 10-hour test run, the Rubin Observatory identified 214 brand-new asteroids, hinting at how much it could improve the way we search for interstellar objects. Some scientists have gone even further and proposed using NASA's Mars rovers to take images of 3I/ATLAS as it passes near Mars in October. This would give us a rare view of an interstellar object from the surface of another planet. To understand why 3I/ATLAS is drawing so much attention, it helps to consider what these interstellar visitors can reveal. Objects from beyond our solar system carry clues about the environments they came from, almost like messages from faraway stars. By studying their makeup, scientists get insight into the materials that formed other planetary systems. For example, spectroscopic tools can help analyze the surface or coma of 3I/ATLAS and determine which molecules or elements it contains. The James Webb Space Telescope's infrared technology can also detect heat given off by the object. This could tell us more about what it's made of. If it's a comet, we might find water, carbon dioxide, or other frozen gases. If it turns out to be an asteroid, it might be dense and metallic, possibly altered by billions of years of exposure to cosmic radiation, similar to theories around Oumuamua. Finding 3 interstellar objects in under 10 years has surprised many scientists. Before Oumuamua, the estimate was that one such object might enter the inner solar system once a year. but they were likely too small or too fast to be detected using older equipment. Now, thanks to modern observatories like Pan-STARRS 1, ATLAS, and the Rubin Observatory, we're spotting them more often. This has led to the idea that these visitors might actually be more common than once believed. Susanne Faltermeyer, an astrophysicist at the Jülich Supercomputing Center in Germany, explains that passing stars or massive planets can knock small objects out of their systems, sending them drifting through the galaxy. Some of these may be planetesimals, early building blocks of planets, giving us a closer look at how other solar systems began to form. The mystery around these objects often sparks speculation. Oumuamua's unusual shape and movement led to theories that range from chunks of nitrogen ice to alien spacecraft. In 2021, one study suggested that Oumuamua might have been a fragment of an exo-Pluto, a planet similar to Pluto from another system, made of nitrogen ice that turned into gas as it approached the Sun. That theory could explain its shape and motion, but Loeb and other experts have questioned its accuracy. Likewise, the unusual brightness and large possible size of 3I/ATLAS have drawn comparisons to science fiction stories like Arthur C. Clarke's Rendezvous with Rama, which describes a huge spacecraft moving through our solar system. While natural explanations remain the most likely, the lack of firm answers continues to leave room for alternative ideas. At the moment, 3I/ATLAS remains a mystery, but it's one we're now more prepared than ever to investigate. Its discovery comes at a time when technology is evolving quickly, giving us the tools to examine these objects in greater detail than before. Amateur astronomers have been playing a significant part in this effort. Sam Dean's identification of earlier images of Atlas, taken between June 25th and 29th, helped improve calculations of its orbit and confirmed that it came from beyond our solar system. Today, skilled amateur astrophotographers are already managing to capture 3I/ATLAS, even though it currently shines at a faint magnitude between 17.5 and 18.8, only visible through high-powered telescopes. By August, it's expected to brighten to magnitude 16, allowing more observers to spot it. These efforts highlight how modern astronomy is becoming increasingly collaborative, with both professionals and amateurs working together to understand what's out there. As 3I/ATLAS makes its way toward the Sun, scientists will be paying close attention to how it behaves. If it's a comet, we may see it develop a coma or tail as it heats up, suggesting it's made of ice. But if it stays unchanged, similar to Oumuamua, then it could be a rocky object or something entirely different. Since it's moving at 66 kilometers per second, around 150,000 miles per hour, we only have a short window to examine it before it exits the solar system in 2026. In contrast to Oumuamua, which we only managed to observe for 80 days, and Borisov, which was visible for about a year, 3I/ATLAS gives us several months to collect valuable data. This extended time frame may help settle ongoing questions about its physical size, its composition, and where it came from. What makes this discovery even more important is how it expands our understanding beyond our own solar system. Every interstellar object we identify helps us add to our knowledge of what's traveling between stars. Are these systems like ours, with rocky debris and icy comets? Or do they contain things we've never encountered? The materials in objects like this could help us understand whether the building blocks of life are widespread. For instance, if 3I/ATLAS contains complex organic compounds such as tholins, often found in the outer parts of our own solar system, it might suggest that similar ingredients for life are common across the galaxy. The Rubin Observatory's Legacy Survey of Space and Time, scheduled to begin operations in 2025, could help find many more such interstellar visitors. That would make rare discoveries like this one far more routine. Still, despite all the excitement, there's no need for concern. According to NASA's trajectory predictions, 3I/ATLAS doesn't pose any threat to Earth. Its closest approach will occur in December 2025, and it will pass by at a safe distance. Its hyperbolic orbit also confirms that it won't return. It's simply passing through on its way out of the solar system. This makes it a unique, time-limited opportunity to study something truly foreign. The object's high velocity and unusual orbital path suggest it's been drifting through space for an incredibly long time, possibly after being thrown out of its home system by a close encounter with a planet or star. Its solo trip through the Milky Way, unconnected to any solar system, is a clear reminder of how vast space really is, and how many untold stories are still out there. Though unlikely, the idea of an artificial origin still sparks interest. When Loeb suggested that Oumuamua might have been a probe, it ignited widespread discussion about how we interpret unusual discoveries. His proposal to use the James Webb Space Telescope to observe 3I/ATLAS is part of that same mindset, aiming to either confirm or rule out such theories. But most astronomers, including Matthew Knight from the University of Maryland, believe natural explanations are more likely. Knight, who studied Oumuamua, argues that outgassing from water vapor or hydrogen ice could explain strange accelerations without needing to involve alien materials or technologies. Still, the absence of solid proof keeps the discussion going. Since this object is on a path that takes it back into interstellar space, every new piece of information is precious. Over the next few months, teams around the world will point their telescopes at it. Each image and spectrum they collect will help fill gaps in our knowledge. Observatories in both hemispheres will track its motion. Observers in Chile, Hawaii, Spain, South Africa, and Australia will pass data to a shared network. Amateur astronomers with advanced setups will add measurements of brightness. By combining all of these, we can refine estimates of its shape and rotation. Spectroscopy will play a central role. By splitting the light, it reflects into its component colors. Scientists can detect chemical fingerprints. Signs of water ice, silicates, organics, or metals could appear as dips or peaks in the spectrum. If organic molecules show up, that would tell us more about processes in other planetary systems. If the object's surface is reddened or coated in dark material, that might hint at space weathering from cosmic rays over eons. Thermal observations will add another layer. Infrared telescopes can see how it absorbs sunlight and re-emits heat. That tells us about surface roughness and thermal inertia. A high thermal inertia would mean a dense or rocky surface. A low value would point to a loose, dusty exterior that heats up quickly. Combined with spectroscopy, these readings can sketch a picture of the surface texture and structure. High-resolution imaging is also on the agenda. Adaptive optic systems on large telescopes can correct for Earth's atmospheric blur. This allows them to capture sharper snapshots. If the object has a companion or debris trail, these images might reveal it. Radar studies, if feasible, could bounce radio waves off the object and return data on its size and surface features. This is how NASA mapped asteroid Bennu and Apophis when they approached Earth. While 3I/ATLAS will not come as close, powerful radar arrays might still glean useful signals. Meanwhile, space missions are poised to take note. The Vera C. Rubin Observatory will regularly scan the sky starting in 2025. Its wide-field camera will pick up fainter interstellar travelers and track them over time. Even if 3I/ATLAS fades beyond reach, the patterns we see now will guide how we spot and follow future visitors. Other projects, like the European Space Agency's Comet Interceptor mission, could benefit from these lessons. Comet Interceptor will travel to a distant point and wait for a new visitor. The experience with 3I/ATLAS will inform trajectory planning and instrument readiness. On the public front, citizen science portals will open. Websites like Zooniverse may offer projects where volunteers classify images or flag brightness changes. These efforts multiply the eyes on the sky. A single brightening event could go unnoticed if we rely only on a few professionals. But with thousands of volunteers, anomalies stand out more quickly. This kind of crowdsourced science has worked before. It helped discover exoplanets in Kepler data and minor planets in Hubble images. Now it can help with interstellar objects too. Educational outreach will ramp up as well. Planetariums and science centres will host talks and live streams. Students at high schools and universities will include 3I/ATLAS data in projects. They might model its orbit in physics classes. They might run simulations of how it would behave if it had jets of gas like a comet. These hands-on experiences can inspire the next generation of space scientists. Media coverage will keep the public informed. Short articles, social media posts and podcasts will summarize the latest findings. Writers will explain what spectra or light curves mean without jargon. Whenever a new peak appears in a spectrum graph, they will show a simple chart and note what molecule it represents. Listeners will hear about temperature estimates or rotation periods in everyday language. This way, people around the globe can share in the process of discovery. Behind the scenes, data analysts will work on models. They will run simulations of different scenarios. A rocky body ejected from a young planetary disk might have different surface features than an ice-rich comet flung out by a gas giant. By comparing simulated light curves to the real ones, analysts can test which scenario fits best. This modeling often involves machine learning tools. Training algorithms on samples from meteorites and asteroid fragments can sharpen predictions. Researchers will also revisit past interstellar discoveries. By comparing 3I/ATLAS to Oumuamua and Borisov, they can look for patterns. Do all interstellar visitors share a similar range of speeds or trajectories? Do they come from certain directions in the sky more often? Is there any clustering in their chemical makeup? These questions require a statistical approach. With 3 objects now, the sample is still small, but each new visitor increases the sample size. Over the next decade, we might build a database of dozens. Then we can ask stronger questions about where interstellar objects originate and what they carry. One intriguing line of inquiry focuses on the outer reaches of exoplanetary systems. In our own solar system, the Oort cloud extends tens of thousands of astronomical units from the Sun. Other stars may have similar reservoirs of comets and objects. Gravitational nudges from passing stars or galactic tides could kick some of these bodies out into interstellar space. By studying incoming objects, we can infer the properties of those distant cloud regions. For instance, a high fraction of icy bodies would indicate a cold formation zone. A mix of rocks and organics would suggest more varied conditions. As this work unfolds, it will spark new questions. Could an interstellar object ever be captured into our solar system by a chance encounter? Some models show that, under the right conditions, an object could be slowed enough to become bound. If one were captured, it might settle into an unusual orbit around the Sun, or even a planet. Finding such a captive would open up a treasure trove. We could send spacecraft directly to study it at close range. Proposals for mini-missions have already appeared in journals. Engineers have sketched designs for small probes or CubeSats that could dart toward an incoming interstellar target. While none have been greenlit yet, the case of 3I/ATLAS strengthens the argument. International cooperation will be vital. Data sharing between NASA, ESA, JAXA, CNSA, and other agencies will speed progress. Clear protocols for alerting the community will ensure that observers worldwide can pivot to follow the object. Standardized formats for reporting brightness, spectra, and position will reduce confusion. At the same time, open access to raw data will let independent teams reanalyze results. This transparency builds trust and accelerates discovery. In the months ahead, the story of 3I/ATLAS will unfold in real time. As it nears its closest approach to Mars, planetary scientists may examine whether it experiences any gravitational effects. Will the red planet's gravity alter its course slightly? Will tides from Mars induce any activity on its surface? While Mars is small, its proximity could produce measurable changes in trajectory. Those shifts can reveal details about the object's mass and density. When the object finally draws near the inner solar system, space-based telescopes may get snapshots free from atmospheric distortion. Instruments on Hubble or its successors could capture ultraviolet or near-infrared spectra that ground telescopes cannot. Those data points could confirm or rule out certain materials. A sudden spike in ultraviolet absorption might indicate the presence of volatile gases. Then, as it passes back toward the outer regions, the trail of observations will provide a record of its journey. Scientists will publish papers detailing its light curve, spectral signatures, and orbital evolution. Conferences later in the year will feature talks on the object's origin and structure. By comparing notes, researchers will refine their models and perhaps publish a special issue in a major journal dedicated to interstellar objects. We stand at the threshold of regular interstellar astronomy. With each new guest, we will deepen our knowledge of the galaxy. For now, we watch, we measure, and we wonder what secrets 3I/ATLAS will reveal before it returns to the dark reaches between the stars. Thanks for watching, and we will see you in the next video.